welcome to the channel. In this tutorial, we will walk through a chess application built in the Rust programming language. The user interface is built with eGUI and eFrame. The chess rules come from the ChatGPT crate, and the piece graphics are embedded SVG files that are converted into textures at runtime. Instead of beginning with the largest source file, we'll follow the application in a logical order. Project dependencies, program entry point, chess rules and game state, asset loading, board rendering, pawn promotion, top-level application logic. That order makes it easier to understand how each layer supports the next one. Okay, let's start with the project dependencies. So I've got VS Code open, and I'm just going to go and build this app. I'm not going to type in all the code. I'm just going to go ahead and I am going to create the files that we need and then copy and paste the code in here so you can see. And feel free to pause it at any time and type in the code if you like, and I will wait for you if you pause the video. Alright. Now, so I just created a Cargo.toml, as you can see over here. If you have VS Code, you can just click over there and create a new file real quick and easy like that. And then I'm just going to copy this stuff in here. I'm not going to make you watch me type it in. Alright. So eFrame provides the native desktop application framework. It creates the operating system window and runs the event loop. eGUI is the immediate mode GUI library used to build the interface. Buttons, panels, windows, labels, and custom board drawing all come from eGUI. Now ChatGPT is the chess rules engine. It represents the position, generates legal moves, detects checkmate, and creates standard algebraic notation. The remaining graphics crates handle the SVG artwork. Oh, and by the way, these are all crates. These are all Rust crates. Alright, let me type it in. Rust crates. That's what these are. Alright. And basically a crate is just a collection of code. It's kind of like a library. If you're familiar with other programming languages, it's basically similar. And if it wasn't for these, we would have to type up a lot more code. We'd have to solve a bunch of problems that have already been solved over and over again every time we wrote the code. But luckily, someone already did it for us and gave it to us for free, so here we go. Alright, moving on. USVG parses SVG data. RESVG renders the data, and TinySkia, this little crate down here, provides the pixel buffer that receives the rendered image. Finally, Anyhow provides convenient application level error handling. Alright, and finally we've got some more code at the bottom of this here. Boom, we've got a little section down here. Now, the release profile optimizes the final executable. Optimization level 3 enables aggressive compiler optimization. Link time optimization allows optimization across crate boundaries. And strip removes unnecessary symbol information from the finished binary. So basically, this is just for the compiler to, instructions for the compiler. And this is also instructions for the compiler, so it gets the version correct of each of these crates. So if, undoubtedly these crates will be updated probably in the future. So they're going to have different numbers in the future, but this will make sure we always get the same version of the code they were expecting. So that's essentially that. And then up here, this is just the name of our app, chess-app. The version, I believe that's the Rust version. And edition, I believe that's the year of the Rust edition. But usually don't have to really worry about that too much. And also, I generated all this with ChatGPT, Codex. So if you're doing that, then you don't really have to worry about this too much. Just be aware that this is here. And After this, we're going to move on to the native entry point. Okay, so next I'm actually going to paste an assets folder. Now, you're going to have to find your own assets. I have the code for this on GitHub with the assets as well. If you want to check it out, download that and use that. So this has all my pieces, like the bishop, king, knight. These are just SVGs. As you can see, B for black bishop, B bishop, or W bishop for white bishop. Don't really need white and black, you just need two different colors to basically tell the two teams apart. Or your two players. Then also have the squares here. This is going to become the chessboard. So we got a brown square, purple square, got a gray square. Then we got a tropical square, as you can see. And those are also SVG files created. I created these with ChatGPT as well. All right, moving on. So first thing we're going to do here, create a source. So we're going to create a source folder. And then inside that source folder, we're going to create a main.rs. And rs is the Rust file extension. And then we're going to copy this code in here. So, the entry point file begins by declaring the project's 5 modules. The app module coordinates the whole interface. The game module owns the chess position and rules. The board module draws the chessboard. The assets module loads and caches the SVG graphics. And the promotion module displays the pawn promotion dialog. We then import the top-level chess app type and the viewport builder used to configure the native window. Section of the code. Here it is. Now the main function returns an E-frame result, as you can see here. That means errors from window creation or the native event loop can be returned directly to the operating system. The native options value configures the desktop window before the interface begins rendering. The initial size is 900 by 720 pixels. The minimum size prevents the window from becoming too small for the board and sidebar, and the title is set to Chess App. The remaining options use E-frame's default. Run native starts the native event loop. The closure is called once the application starts. Inside that closure, we construct a new chess app and place it inside a box. The creation context gives us access to the eGUI context, which is passed into the application constructor. From this point onward, the framework repeatedly asks the application to draw the next frame. Before looking at buttons or board graphics, we need to understand the actual chess model. This module deliberately separates chess rules from interface behavior. The UI does not decide whether a move is legal. It asks the game model, which delegates the rule-heavy work to Shakmati. Alright, next we're going to create a new file. We're going to call it game.rs and make sure it's in the source folder along with main.rs. And I'm going to copy paste the code. Now the application defines its own high-level game outcome enum. This gives the interface a simple set of states to display without exposing every detail of the underlying chess library. Checkmate stores the winning color. The other variants represent the draw conditions supported by the application. Stalemate, insufficient material, the 50-move rule, and threefold repetition. Alright, here's the next part of the code. Every completed move becomes a move record. The sand field stores standard algebraic notation. The original move is retained for features such as move highlighting and CSV export. The previous chess position is also stored. That snapshot makes undo straightforward because the game can restore the exact earlier position. Alright, next part of the code. The game struct contains 3 pieces of state. Position is the current chess piece position. History contains every move that has been played. Repetition counts tracks how many times each complete position has appeared. That is necessary for detecting threefold repetition. Using the complete chess position as the hash map key means repetition tracking includes the information relevant to the legal position, not just the visible locations of the pieces. So the chess default creates the standard starting position. The starting position is immediately inserted into the repetition map with a count of 1 because it has already occurred once before either player moves. And so that's this right here, repetition counts, insert position.clone, and the move history starts empty. Bam. Now, moving on to the next part of the code. Let me get that here. Boom. All right. These methods expose small, focused pieces of information to the user interface. PSAT checks whether a square contains a piece. Side to move returns white or black depending on whose turn it is. This is preferable to letting the interface reach deeply into the checkmate position everywhere. Alright, checkmate generates every legal move in the current position. The interface normally needs a smaller set. All legal moves belonging to the piece the player clicked. This function filters the complete move list and keeps only moves whose starting square matches the selected square. The result is later used to draw the legal move markers on the board. Alright, once the player selects a source square and then clicks a destination, the application asks for all legal moves between those two squares. Normally, this vector contains either 0 or 1 move. Pawn promotion is the important exception. A pawn moving to the final rank can promote to a queen, rook, bishop, or knight, so several legal moves can share the same source and destination. That is why this method returns a vector instead of a single optional move. The play method first validates the move. Even though the user interface normally supplies moves from the legal move generator, validating again protects the model from incorrect callers. Before changing anything, the current position is cloned. This snapshot will be stored for undo. The move is also converted into standard algebraic notation before the position changes because SAN depends on the pre-move position. Finally, checkmate applies the move and returns the new position. After the move succeeds, the current position is incremented and a move record is added to the history. This single method keeps the position, repetition tracking, SAN history, and undo data synchronized. Undo begins by removing the latest move record. The question mark operator returns none immediately when the history is empty. Because the current position is being removed from the active history, its repetition count must also be decreased. The earlier position is then restored directly from the saved snapshot. This approach is easy to reason about because undo does not attempt to reverse each special move manually. Castling, promotion, captures, and en passant are all restored by replacing the entire position. The outcome checks are arranged from the most decisive condition to the broader draw rules. When the current player is checkmated, the winner is the opposite color because position.turn still represents the player who cannot move. Next, the model checks for stalemate and insufficient mating material. And now the 50 move rule is measured in half moves, also called plies. 50 moves by each side equals 100 plies, so the application checks whether the half move clock has reached 100. Threefold repetition is detected by looking up the current position in the repetition map. When no ending condition applies, the function returns none. The move list is exported as a plain string, so this project does not need a separate CSV dependency. Each row includes the move number, side, starting square, destination square, and sand notation. The CSV escape helper handles values containing commas, quotation marks, or line breaks. Now that the chess model is clear, we can move into the presentation. Now, let's create a new file. We're going to call it assets.rs. Make sure we move it into the source folder. The asset module embeds the SVG files in the executable, renders them into pixels, and caches the resulting eGUI textures. And here's our first bit of code. Alright, board theme represents the 4 available board styles. The derived hash and equality traits allow a theme to become part of a cache key. And the next section of code. Alright. An asset key identifies either a board square or a chess piece. A square is identified by its theme and whether it is light or dark. A piece is identified by its color and role. This creates a type-safe identifier instead of relying on file path strings throughout the program. Alright. Now, the cache key contains both the logical asset and its requested pixel size. The size matters because the board can resize with the window. The same SVG may need to be rendered at different resolutions. Alright. And let's see if we could see all this in one. Let's close that. There we go. Alright. So, first time an asset is requested at a particular size, its SVG bytes are rasterized. The resulting image is uploaded to eGUI as a texture and inserted into the cache. Every later request for that same asset and size returns the existing texture handle. Without this cache, the application could repeatedly parse and rasterize SVG files every frame. Now this next section of code's fairly long, and this is going to basically pull in all of the SVGs that we have in our assets folder. As you can see, the names match up with the path names right here, and so the path names are hard-coded. So your path names need to match whatever the names are of the SVGs in your assets folder are. That's basically for this to run smoothly. So, include bytes right here. This include bytes runs at compile time. The contents of each SVG file are embedded directly into the executable, so the finished application does not have to locate those files at runtime. The complete match covers every board theme and all 12-piece combinations. And you can find this code on GitHub as well. Link is in the description. Alright, moving on to the next section. Here it is, the rasterize SVG function. The SVG data is first parsed into a USVG tree. A square RGBA pixel buffer is then allocated using TinySkia. That's the TinySkia crate. Let me get the next section of code. And also feel free to pause the video anytime. I will wait for you if you do pause it. And then you could type in this code if you're following along. If you like typing things out with your fingers. If you like, carving the text out of the stone with your fingers or whatever. So the scale uses the smaller of the horizontal and vertical scale factors. That preserves the SVG's aspect ratio and ensures the complete graphic fits inside the square texture. The X and Y values center the rendered SVG. Alright, let me get the next. Let's get the last part of this function up on the screen. Here we go. Alright, there's the full function. I pasted it in a few different parts so that you could see it all on the screen, because I have a really small screen that I'm using right now. Alright, let's get back on the subject. RESVG, that's RESVG, renders the tree into the pixel buffer for me. The raw RGBA data is then converted into an eGUI color image, which can be uploaded as a texture. Alright, so this basically converts all of our SVGs into textures at runtime. Okay, the next thing we're going to do is create a board.rs. We're going to double click over here in our sidebar if you're using VS Code. And if you're not, well, just do whatever you got to do to create a new file. There, we got board.rs. Make sure it's in the source folder along with the other files we've created so far. So when the compiler looks for all this stuff, it's going to look inside the source folder, and then it's going to look for the name of our files. All right, let's get the code in there before I get off topic. Now, board view, the struct board view, contains everything required to draw one frame of the board. The board borrows the game rather than owning it. It also borrows the asset store, receives the selected theme and orientation, and gets the current selection and legal destinations from the application layer. This keeps the board focused on rendering. It does not own the chess game or decide how clicks modify it. Alright, so let's get the next section. Board response. The board's output is intentionally small. It reports which chess square was clicked, if any. The top-level application decides what that click means. Alright, next section of code. Come on through. Boom. The board uses the smaller available dimension, so it always remains square. Allocate exact size, reserves that square region, and creates an interaction response capable of detecting clicks. Alright. Paint order matters because later drawing operations appear above earlier ones. The square textures form the background. The last move and legal destinations are drawn next. Pieces appear above those markers. Coordinate labels are drawn after the pieces, and the checkmate overlay is painted last, so it covers the entire board. Alright, next section of code. Here we go. Alright, the nested loops visit all 64 screen positions. It is important to distinguish display coordinates from chess coordinates. Display coordinates describe where a square appears on the screen. The displayed square helper converts that location into an actual chess square while accounting for board orientation. The sum of the display file and rank determines whether the square uses the light or dark texture. Alright, let's get the next section of code. Hang in there. Boom, copy, paste. Alright. There we are. Try to get it all on the screen. Here we go. It's all on the screen. The selected piece receives a gold outline. When keyboard controls are enabled, the keyboard cursor receives a separate cyan outline. So that's a gold outline right here. That's RGB values, red, green, blue values, number values. And the other one is a cyan outline. Alright. Using two visual treatments allows the cursor and selected piece to represent different states. So that way if you're clicking with the mouse or if you're using the keyboard, it's visually clear that you're using the keyboard to move your pieces rather than the mouse, or vice versa. Alright, next section of the code. Copy, paste. There we go. Alright. So, legal moves use two marker styles. An empty destination gets a small filled dot. A destination containing an opposing piece gets a larger ring around the piece, clearly indicating a capture. So this is basically a move preview. When you click on your piece, you'll see some little dots. It'll tell you where the piece can go. And then it'll show you if it's going to capture a piece or not at the end of its move. Pointer coordinates are measured in pixels from the top left of the interface. Subtracting the board's top left corner gives a position relative to the board. Dividing by the square size gives a file and rank between 0 and 7. And let's get the next section up. Boom. Alright. Now, okay. After a bounds check, the display location is converted into a real chess square. This final conversion is what makes the same click logic work in both normal and flipped orientations. Alright, we're going to create another file. We're going to call this promotion.rs. So just got to double click on the sidebar over here. Make sure this is in the source folder as well. In fact, all the files we're going to create are going to be in the source folder, except for the assets folder. That's going to be its own separate folder. And then these two folders should be in a main directory, whatever you want to call it. I called mine chess app. But and then of course you need your Cargo.toml file, which we created earlier. All right, moving on. We got our promotion.rs. Let me copy the code. The promotion interface is separated into its own small module. Like the rest of eGUI, this window is rebuilt every frame. Chosen role starts as none and only receives a value during the frame in which the user clicks a button. Alright. The 4 promotion choices are stored in a small array. And looping over that array keeps the button construction consistent and avoids repeating nearly identical code. The function returns the selected role to the application layer. Okay, next we're going to create another file. We're going to call this app.rs. We're going to double click over here. And then this is also going to go in the source folder. And first of all, we're going to copy and paste quite a bit of code here. So this is the chess app struct. And I've got some comments in here. Now if you download this from GitHub, all of the code will have plenty of comments. So it'll explain what it does as well, so you can go more in depth in case my in case my explanation doesn't satisfy. But yeah, so check it out on GitHub, links in the description. Now, let's talk about the chess app struct. The fields can be understood in groups. First, the application owns its core services, the asset store and game model. Next comes interaction state, the selected square and its legal destinations. Then there are user preferences such as board orientation, theme, previous move highlighting, and keyboard controls. The timer fields track both clocks and the latest timer update. Finally, the App Store's modal state and recoverable messages. This persistent struct is what allows an immediate mode interface to remember information between frames. Next section of code. Selecting a square does two things. First, it stores the selected square. Second, it asks the game model for every legal move beginning there and converts those moves into destination squares for rendering. The board does not need the complete move objects just to draw markers. It only needs their destination squares. Alright, clicks are ignored while a promotion decision is open or after the game has ended. This prevents the board position from changing behind a modal or after checkmate. or draw, or a timeout. And next section. All right. Clicking the selected square again cancels the selection. Clicking another friendly piece changes the selection to that piece. This makes the interaction feel natural. The user does not have to manually cancel one selection before choosing a different piece. To attempt a move, a starting square must already be selected. The game model returns every legal move connecting that source to the clicked destination. An empty vector means the destination is illegal, so the function does nothing. And next section of code. Multiple candidate moves indicate promotion. The candidates are saved and the promotion modal is opened. For a normal move, there is exactly one candidate, so it can be played immediately. Alright, the application passes the move into the rules model. On success, selection markers are cleared, the clock tick is reset, undo becomes available, and old messages are removed. On failure, the error text is stored for display in the sidebar. The model performs the validation. The user interface only reacts to the result. The timer only runs when 4 conditions are satisfied. Timed mode must be enabled. At least one move must have been played. The chess game must not already have an outcome. And neither player may have already run out of time. Resetting last timer click during a pause prevents a large stale time difference from being charged when the timer resumes. All right. The clock uses instant, which is appropriate for measuring elapsed time. Replace stores the new timestamp and returns the previous one. On the first timed frame, there is no previous timestamp. So the app requests another repaint and waits for the next frame. Only the player whose turn it is loses time. The match returns a mutable reference to that player's remaining seconds, allowing the shared subtraction logic to work for both colors. The result is clamped to 0, so the clock cannot become negative. At the beginning of each frame, the application updates the chess clock and processes keyboard input. The remainder of the function constructs the visible interface using the updated state. Alright. The control panel is placed on the right side and given a fixed minimum width. It is not user resizable. A vertical scroll area ensures the controls remain accessible even when the application window is short. The sidebar contains the game status, chess clocks, move history, new game button, board controls, undo, CSV export, and theme selection. Alright. Moving on. Alright. The central panel contains the board. All rendering options are packaged into a board view and passed to Show Board. Notice how the board receives immutable access to the game, but mutable access to the asset cache. The game is only being read during rendering, while the asset store may lazily add a texture to its cache. Alright. The board can return either a successful response or a rendering error. When a square was clicked, that square is passed into the application's click state machine. If an SVG cannot be loaded or rendered, the error is stored and shown in the sidebar. After the main board and sidebar are drawn, the app handles its modal interfaces. The promotion picker appears when promotion candidates are pending. The new game confirmation dialog resets the game only after confirmation. The timeout overlay is drawn last, placing it above the rest of the interface. Alright, let's get the next section up here. Normal moves and en passant are already contain the destination square expected by the player. Castling requires special handling. Internally, the Shakmati crate represents castling differently from the way a player normally describes the move. The user interface converts it into the king's final square on the C file or G file. That conversion keeps board highlighting, click behavior, and move list output aligned with standard chess expectations. The main design strength of this application is its separation of responsibilities. The main.rs creates the native window. Game.rs owns the chess rules, position, history, undo system, and outcomes. Assets.rs embeds and caches the SVG artwork. Board.rs draws the position and translates pointer coordinates into chess squares. Promotion.rs handles one focused modal interaction. And app.rs connects everything together by owning the persistent user interface state and deciding how user actions affect the game. Now, if you want to start this app up, all you gotta do is open up a terminal, and if you have Rust up installed and you have Cargo installed on your system, which I'm using Cargo and Rust up and all that good stuff that comes with it, this will compile the app and start it up for us all in one simple command. So I'm just going to press enter. Now the first time you run this, it's going to take a while, more than likely. Depending on your system, it's got to download a bunch of crates, and then it's got to compile all that stuff and get it all ready to go. So it might take a few minutes the very first time we do that. Just keep that in mind. I'll probably cut out a section of this. But as you can see, these are all the dependencies, all the extra code that we need to run this app. And if it wasn't for all this free code, I would have to write a lot more code to make a simple chess app. A lot more, code than just these few modules we have here. So while that's going, I'll go ahead and close out the video. And then you'll see the result at the end of this. As you can see, it's got 209 crates it's got to build. Okay. So that separation makes the project easier to understand, test, and extend. For example, a computer opponent could be added to the game layer, drag and drop could be added to the board layer, and additional settings could be added to the app layer without rewriting the entire project. That is the complete architecture of this Rust chess application. Alright, so the chess app started up here. Let me maximize this and hide my face. Okay. So it's basically a pretty simple chess app. It starts with the white on the bottom. You can flip the board by clicking this button over here. If you want black on top or black on the bottom, whatever. You can change the color of the board with a click down here in the right hand corner, the bottom right hand corner. There's different options for that. Could choose a timed game, custom amount of time, or 1 minute, 3 minutes, 5 minutes. Alright, so if you want to start the game, just click on a white piece, boom. Now it's a timed game, so the clock is ticking. Then you can just click on that, and it'll actually show you the moves you can make with the pieces. These little dots are potential moves you can make. And as you can see, so it's basically a pretty simple chess app. Nothing too fancy. I think it's pretty cool. Alright, if you like this content, go ahead and subscribe. That really helps the channel grow. And leave a comment below if you would play this game with your friend. And also let me know in the comments below if you would like me to add a chess engine to the game so you could play with a computer opponent. And yeah, just subscribe and leave a comment. And that's all, folks.